So you are using iPad or something else, or laptop?
Sorry.
So are you using the iPad or laptop here? I mean,
Okay.
iPad. I mean.
Yes. Yeah.
Okay.
I use iPad Pencil.
Looks very nice.
Thank you very much.
Yeah. Okay, so are you ready? Okay, so today I'm very happy to introduce Dr. Shou Yoshikawa from the University of Tokyo. He will talk about the structure of varieties admitting an int-amplified endomorphism. Okay, you may begin. Thank you.
Thank you very much for introduction, and I would like to thank Professor Mayer for giving me this opportunity and organizing this really nice conference. Thank you very much. And today I'd like to talk about the structure of varieties admitting an int-amplified endomorphism. And in this talk, all varieties and morphisms are defined over algebraically closed field K in characteristic 0. Okay. First of all, we recall the definition of int-amplified endomorphisms. Let X be a normal projective variety, and the finite endomorphism F is called int-amplified if F H minus H is ample or some ample quality divisor H. And we note that toric varieties and abelian varieties have int-amplified endomorphisms. And if X and Y have an int-amplified endomorphism, then X times Y has an int-amplified endomorphism. So we consider the class of varieties admitting an int-amplified endomorphism. Then this class contains toric varieties and abelian varieties. And this class is closed under taking fiber products. Now I want to answer the following question. Let X be a smooth projective variety admitting an int-amplified endomorphism. This is smooth and admitting an int-amplified endomorphism. In this case, taking some equivariant étale cover, X tilde of X is every fiber of the Albanese morphism toric. Where this equivariant means some iteration of F induces the endomorphism of X tilde. And this cover is equivariant under FM and G. This is the first question. And second question is that if X is rationally connected, then is X toric? So we note that the answer of the first question is yes. If the answer of the first question is yes, then the answer of the second question is also yes. Indeed, if X is smooth and rationally connected, then this cover is trivial. And the Albanese morphism is constant. So X is toric. And Next, I introduce the related results. The thing is same as question. X is smooth projective variety admitting an int-amplified endomorphism. In the first, Fujimoto and Nakayama classified the smooth surfaces admitting a non-invertible endomorphism. By this classification, we obtain the smooth surface case. And Fakhruddin proves that if X is non-uniruled, then X is Q-abelian. Q-abelian means X is ethyl quotient of abelian variety. And Huang and Mock proves that if X is Fano threefold with Picard rank 1, then X is projective space 3. And next, Professor Mei and Professor Zhang and Professor Zong proves that if F has the totally invariant ramification locus and X is rationally connected, then X is toric. And Professor Mei and Professor Zhang proves that taking some equivalent ethyl cover X shield of X, every fiber of the Albanese morphism is smooth, connected, and rationally connected. And in this talk, I introduce the stronger version of this theorem. Indeed, we replace this property, rationally connected, into phenotype. So next, we recall the definition of phenotype. We need the notion of relative phenotype, so we consider the relative setting. Let X to be, this is a morphism of normal projective varieties. In this case, X is called phenotype over B if for some effective QP divisor delta on X such that minus KX plus delta is ample over B, and this pair is KLT. And this pair is called log phano pair over B. And X is called over Calabi type over B if for some effective QP divisor delta on X such that KX plus delta is relative numerical trivial and X delta is log canonical. In this case, this pair is called log Calabi pair over B. We note that phenotype over B implies Calabi type over B. And toric varieties are of phenotype over a point. But in this case, we omit saying over a point. And the Albanese varieties are of Calabi type. And Brasset and Gongyo propose the following conjecture. If a normal projective variety X has an int-amplified endomorphism, then X is of Calabi type. So we assume only the normality. Only assume the normality. And this conjecture is proved by the normal subscale. If this endomorphism is polarized, Brasset and Gongyo prove that. And in the amplified case, I prove this theory. And this is the main theorem in this talk. The setting is same as question. X is a smooth projective variety admitting an int-amplified endomorphism. In this case, taking some equivariant data cover x tilde of x tilde is open type over the Albanese variety of x tilde. In particular, if x is rationally connected, then x is open type. Okay. We know that we can prove that every fiber of the Albanese morphism is open type. But I omit the details of this statement. And in general, phenotype implies rationally connected. So this theorem means that if X admits int-amplified endomorphism, we obtain the converse direction. And Brasset and Gonbios conjecture calls for smooth and rationally connected varieties. This is the main theorem in this talk. And first, I introduce the steps of the proof of this theorem. The setting is same as the theorem. And in the first step, running suitable equivalent MMP, we obtain the following equivalent sequence, like this. Where this delta I. Delta I is a suitable boundary on xi, such that xi delta I is KT. And the kxi plus delta I is not effective for I less than I. And xi to xi plus 1 is a kxi plus delta I MMP. So this is a composition of birational map and modifiable space. And the kxr plus delta R is Shou effective. And this sequence is equivalent under some iteration of F. This is proved by Professor May and Professor San. So in this step, the construction of delta is essential. And by step 1, we obtain this equivalent sequence. And in step 2, we construct an eternal cover of X. First, we take a suitable equivalent finite morphism from abelian variety to XR, like this. And we lift it to X as an equivalent eternal cover. So we note that this is not necessarily eternal in codimensional. Not necessarily eternal in codimensional. In this case, since X tilde is smooth and A is abelian variety, this rational map is a morphism. So in particular, this rational map is also morphism. So by step 2, we obtain the following commutative diagram. And in the last step, we prove that X is quantized over XR.
Yoshikawa-san,
Yes.
may I ask a question?
Of course.
So you have this MMP, the construction of delta. So do you construct this MMP first, then you define your delta, or so your MMP is pure MMP, or I guess your delta is constructed by taking this ramification coefficient, right? So so you have MMP first,
Yes.
then you construct delta, right? You
So
first have MMP, then you construct your delta, right?
yes.
So the MMP you have, then you choose delta, then this sequence still log MMP, right? So initially it's K negative, now it's K plus delta negative, right?
Yes. Exactly.
So your delta depending on your X. So delta 1 and delta 2 may not be related. I mean, delta 2 is kind of delta 1 plus something, like this.
Yes, exactly.
Yeah. Okay, thanks.
But if the first several steps are birational, then if you're starting from pure MMP, the first several birational maps, you don't have delta, I guess. The first delta 1 appears when final contraction involved, I believe. I mean,
yes,
for the
first birational map, and
if the first several steps are birational, then you don't have a delta.
yes.
Until the first final contraction appears, then you need to contraction delta 1 here. So x1 has smaller dimension than x, I guess.
Yes, exactly. And so first we obtain we consider this KXMMP, and we construct delta 1 on xi, and next we consider 1 plus delta 1 MMP. We consider this process.
I'm sorry, Yoshikawa again. So you say you construct your delta. So
yes.
Oh, it's still okay. I mean, in the case of pure MMP, you can reach a point in a smooth rational connect case. If we start a pure MMP, you can reach a point. If you do the
no, you cannot reach because you have final contraction involved. Once you have final contraction, you need to add some delta 1 here. This is worse.
So, no, that you use smoothness. So eventually,
but smoothness you still can have some final contraction in your MMP. Although the pure MMP can go to a point.
So let's assume the pure MMP can reach a point, then then the log MMP may not reach a point. But he may not assume this, I guess. He doesn't care. I guess. He just go to a Q final, a Q torus, I guess, Q abelian, I guess.
Yeah.
He doesn't care, you go to reach a point or not. He doesn't care, I guess. He just go to Q torus. I guess.
Yeah.
Okay.
Yeah.
Thanks.
Thank you very much. The later I introduce the definition of delta. This is the steps of the proof, and first we consider the step 1 and step 2. Later I will consider step 3. Step 3 is a technical part of this proof. Okay. So next we consider how to construct boundaries and covers. To do this, we consider the following computer diagram. First, we fix positive integer m larger than 1. And this E is an elliptic curve. And this mu is a quotient by -1. Then we obtain a projective line. Okay. And multiplication in this is the endomorphism of a projective line denoted by H. And mu tilde is a quotient by sigma times -1, where sigma is defined by this formula. So sigma times -1 defines an involution of projective line times this elliptic curve. And the G is defined by G prime times M, where G prime is defined by this formula. Then G induces the endomorphism of X denoted by F. Okay. So we obtain this equivariant commutative diagram. In this case, first F is int-amplified, and mu tilde is causator but not etal by computing the fixed points. In particular, in this case, X is not smooth. Okay. And this pi is a modifiable space. And this X is rationally connected, but not of one type. Okay. So, and this commutative diagram is similar to the diagram in step 2. Indeed, this X is not of one type, but taking covers, P1 times E is one type over the Algebraic variety E. And we observe the relationship between this mu, this cover, and this pi, fibrillation pi. Let Q1 to Q4 are two torsion points on elliptic curve, and Pi is the image of Qi. And delta is defined by 1/2 P1 plus P4. And this divisor satisfies Kp1 plus delta is Q-linearly trivial. And the mu pullback of this divisor is linearly trivial by easy computation. And we define R delta G by the ramification divisor of H plus delta minus H pullback delta, where H is the endomorphism of projective line. And this is equal to the by the computation. Maybe not so easy, a bit complicated. And we note that this divisor is linearly equivalent to Kp1 plus delta minus H pullback Kp1 plus delta. So we regard this divisor as the ramification divisor of the pair. So this notion is very important in this proof. And we can regard this mu as the index 1 cover of Kp1 plus delta. Indeed, Kp1 plus delta is Q-linearly trivial, and the mu pullback of this divisor is Z linearly trivial. Okay. So it means that this mu is constructed by this delta, this divisor. Okay. And this delta is related to multiplicities of fibers of pi, this modifiable space. Indeed, Pi has multiple fibers. Pi has multiple fibers with multiplicity 2. Where this is a reduced fiber. This is the definition. And another point, for another point, it has reduced fiber. Okay.
So excuse me.
Yes.
Why do you write R delta sub G? It involves only H.
Sorry. This is H.
Oh, that should be H. Okay. All right.
Thank you very much. Yes. Sorry. And so this delta is related to the multiplicities of fibers of pi. Okay, in this case. And in this case, the multiplicity of fiber of pi coincides with the ramification of mu. And this equality implies the Fajetariness of mu tilde. The computation, the coefficients of these divisors. P is a close point of a projectile. Referring to this observation, we construct boundaries and cover. Next, we construct delta. We consider equivariant modifiable space pi of KLTQ factorial projective varieties and int-amplified endomorphisms. So X and Y are KLTQ factorial projective varieties, and F and G are int-amplified endomorphisms. And this pi is modifiable space. In this case, we define effective QA divisor delta on Y as follows. Let E be a prime divisor on Y. Then pi pullback E is equal to ME times F for some positive integer ME and prime divisor F on X by using some property of modifiable space. Then we define order E of delta E by 1 minus 1 over ME. So we note that in the example, order P of delta is equal to 0 if P is not equal to Pi, and 1 over 2 if P is equal to Pi. Okay. So this coincides with the delta in example. And we note that except for finitely many prime divisors, order of delta is equal to 0 because the general fiber is reduced. And the definition of delta independence on endomorphisms. So we don't use the existence of endomorphism. Okay. And next, we observe the properties of delta. In this situation, in this setting, we have first Y delta is KLT by Ambrose canonical bundle formula. And this divisor defined by the ramification divisor of G plus delta minus G pullback delta. This is effective. And this is linearly equivalent to KY plus delta minus G pullback of KY plus delta. So we can regard this divisor as the ramification divisor of pair. Okay. And considering this notion, we have this inequality. The ramification divisor of F contains the pullback of the ramification divisor of the pair. We note that in general, the ramification divisor of F does not contain the pullback of the ramification divisor of G. So we need considering the ramification divisor of the pair. And KY plus delta is should effective if and only if KY plus delta is linearly trivial. Because this divisor has effective member. Okay. So in this case, KY plus delta is linearly equivalent to the G pullback of KY plus delta.
Sorry, I have a question. For your second proposition, R delta G by definition is RG plus delta minus G pullback delta greater or equal than 0. And in your bracket, what do you mean? Do you mean 0 linear equivalent to the right hand side?
Sorry.
Should be the
R delta G is linearly equivalent.
Okay. I see.
So this ramification divisor is equal to 0, then we have this linearly equivalent. So this delta satisfies good properties. And we finish step 1. We consider the following sequence. First, this X is smooth projected variety admitting an int-amplified endomorphism. First, we consider KX MMP. If KX is not Shou effective, then this is a composition of birational map and KX prime modifiable space. And we obtain the variety X1. Next, we define delta 1 by using the multiplicities of fibers, like this. And if KX1 plus delta 1 is not Shou effective, we consider KX1 plus delta 1 MMP. Then we obtain new variety X2. Next, we define delta 2 by multiplicities of fibers and the coefficients of delta 1. Indeed, we define order A of delta 2 equal to ME minus 1 plus order F of delta 1 prime over ME. If phi 1 pullback E is equal to ME times F, where phi 1 is this. So we need this term. But the essential part is the multiplicities of fibers. And repeating this construction, we obtain the pair XR delta R with KXR plus delta R is Shou effective. And in this case, we can prove that KXR plus delta R is Q-linearly trivial. Okay, this is step 1. And in step 2, we obtain, by step 1, we obtain this equivariant sequence with KXR plus delta R is Q-linearly trivial. And we consider the index 1 cover of KXR plus delta R denoted by mu. In this case, the ramification divisor of mu is equal to mu pullback of delta R. Because delta R has standard coefficients, it means that every coefficient of delta R is equal to 1 minus m, 1 over m for some positive integer m. Then we can compute the ramification divisor. And by using this property, we have this KW is linearly equivalent, linearly trivial. Because KW is linearly equivalent to Nipple-Back of KXR plus delta. And W is KLT, because this pair is also KLT. And mu is equivalent, because KXR plus delta R is Z linearly equivalent to FR pullback of KXR plus delta R. So by the universality of the index one cover, this FR induces the endomorphism of W. It means that KW is trivial and W is KLT, and W has an int-amplified endomorphism, so W is Q abelian variety. So we obtain Kajeta cover by abelian variety. So we have this cover, finite cover from abelian variety to XR. And we can lift this cover to X as an étale cover, as an equivalent étale cover. And roughly speaking, this étaleness follows from the equality of the multiplicities of the fiber of this morphism and the ramification of this cover, roughly speaking. So in my proof, we lift this cover to xi and xi prime inductively. So we finish step 2. And it is enough to show that X is phonotype over XR. Okay. This is step 3. Next I introduce step 3. And in step 3, we reduce this property to the following 2 cases. Case 1, we assume the existence of this equivalent sequence. And this Y is KLT Q factorial, projective variety, and this Y has int-amplified endomorphism G. And this morphism is KY modifiable space. And this gamma Y is defined by the multiplicities of fibers. Next, we consider KY plus gamma Y, and next morphism is KY1 plus gamma 1 modifiable space. Next, we define gamma 2 by the multiplicities of fibers and the coefficients of gamma 1. And repeating such a process, we obtain YR minus 1, gamma R minus 1, this pair. And the last morphism is KYR minus 1 plus gamma R minus 1 negative extreme Rayleigh contraction. So not necessarily modifiable space. Okay. We assume the existence of this sequence. In this case, Y is open type over Z. And in this case, ramification divisor of G contains some effective relative ample Q-quality divisor. This property is very essential in this case. Later, I will explain this case. And in case 2, we consider, we assume the existence of this equivariant commutative diagram. Where this x, y, z are normal projective variety. We assume only normality. And the FGH are int-amplified endomorphisms.
Oh, sorry for interruption. What was H? The RG is larger than H, larger than 0.
This?
Yeah, what was H? I don't see the definition.
I mean, in this case, there exists the relative ample Q-quality by the H satisfying this inequality.
Oh, okay, I see. And one more question. Could you go back to the previous slide? So you're going to prove H is a phenotype over XR.
This one? Yes,
Yeah.
yes.
What do you mean? So X to X. Oh, is it a morphism?
Sorry, I forgot. I forgot pointing. So since X tilde is smooth and A is abelian variety, so this rational map is the morphism. Okay.
Yeah.
And
so that means
because this is a finite morphism, so this rational map is also morphism.
Okay. I got it.
Thank you very much. Okay. In case 2, we consider the following equivariant commutative diagram. And in this case, y is of one type over z if and only if x is of one type over z. So this property is invariant under equivariant birational map. Okay. So later I will explain these cases. And before that, I explain why these cases are essential. We consider the following simple example. In this case, R is equal to 2. And this X is smooth projective variety admitting an int-amplified endomorphism. And this morphism is Kx modified by space. We obtain the variety X1, and delta 1 is defined by the multiplications of fibers. And we consider Kx1 plus delta 1 flip. We obtain X1 prime plus X1 prime delta 1 prime this pair. And next one is Kx1 prime plus delta 1 prime modified by space. And we obtain this pair. And Kx plus delta 2 is Shou effective. We assume this condition. In this case, we want to prove that X is one type over X2. Okay. In order to this statement, we consider the flipping contraction Z. This flipping contraction is Kx1 plus delta 1 negative X Algebraic contraction. So this sequence is in case 1. So X is of one type over Z by case 1. And in this case, we can run every MMP for X over Z. So running suitable MMP over Z, we obtain bilateral map from X to Y and modify bar space from Y to X1 prime. And in this case, delta 1 prime is delta 1 prime coincides with the divisor determined by multiplicies of fibers. So this sequence is also in case 1. So this Y is on type over X by case 1. And this is equivalent bilateral map. This is equivalent bilateral map over X. So by case 2, we obtain X on type over X. This is a strategy for simple case. So in the general case, this is the sequence of step 1. Okay. And by using case 1 many times, we obtain bilateral map from X to Y. And the composition of modifiable spaces from Y to XR. So we replace this diagram into this by using case 1. Then by case 1, Y is of one type over XR. And by case 2, X is of one type over XR. So we obtain case 3. This is strategy. So next I explain the proof of case 1 and case 2. The key idea is for let F be int-amplified endomorphism of normal projective variety. And degree F is denoted by D. And let X delta is scarcity pair. In this case, we define new boundary delta 1 by the inverse F push RF plus delta. Then this pair is also KLT, and KX plus delta is numerical equivalent to F pullback of KX plus delta 1. This is proved by Fujino and Gongyo. They proved canonical bundle formula for finite morphisms, not necessarily endomorphism. But applying their construction for endomorphisms, we obtain following sequence of boundaries, such that the first one is the definition of delta m. Delta m is equal to the inverse F push RF plus delta m minus 1. And then X delta m is KT, and KX plus delta is numerically equivalent to FM pullback KX plus delta m. And by the construction, delta m contains this effective divisor. Okay. This is independent on m. Using this sequence is key idea. Indeed, first we explain case 1. Case 2. Case 1 is a bit complicated, so first we explain case 2. Case 2 is the setting. In taking elimination of this birational map, we may assume that this pi is birational morphism. And we take a KLT pair by delta, and we define gamma by this formula. In this case, gamma is not effective in general. Yeah. But for large enough M, gamma M is effective. By computing log discrepancy. So if ky plus delta is z numerical relative numerical trivial, then ky plus delta m is also relative numerical trivial. And then this x gamma m is relative numerical trivial KLT pair for enough large m. And if ky plus delta is relative anti-amp, then minus kx is equal to minus kx plus gamma m plus gamma m. This is relative big for large enough m because gamma m is effective. Okay, it means that this x has a relative numerical trivial KLT pair, and minus kx is relative big. In this case, x is a phenotype. X is a phenotype. So we obtain case 2. This claim is very essential. Next, I introduce case 1. Case 1 is the following setting. And in this case, there exists effective Z relative amplitude divisor H on Y. Effective. And this is contained by the ramification divisor of G. So G is endomorphism of Y. And minus ky plus d plus 1 inverse gm pullback H is ample over Z for some n. We can find such a divisor. So in this case, we take general member of this divisor. We find boundary such that y delta is KLT and ky plus delta is Z linearly equivalent to d plus 1 inverse gm pullback H. Then we compute this divisor. Like this. Then ky plus delta m plus 1 is relative numerical trivia, relative numerical equivalent to d plus 1 inverse g push h. So the ampleness is decreasing. Like this. And the delta m plus 1 prime is defined by delta m plus 1 minus d inverse g push h. And then we note that delta m plus 1 is contained. Delta m plus 1 contains the inverse g push r g. And this is contains the inverse g push h. Okay. So this divisor is effective. And since this is effective, y delta m plus 1 prime is KT. And this pair is relative numerical equivalent to this divisor, and this is anti-ample over Z. So we find log fun pair over Z. And the H is constructed by this H1. H1 is contained in this the ramification divisor of pair. Sorry, this Y1 gamma. H1 is divisor on Y1, which is effective relative ample Q-quality divisor. So first, inductively, we prove this statement. And by using this H1, we construct this H. And using this H, we prove Y is of one type.
So what was the assumption on gamma i's?
First, gamma 1 is constructed by the multiplicies of fibers. So like this.
Okay.
And the next gamma 2 is constructed by the multiplicies of fibers and the coefficients of gamma 1, like this.
Oh, okay.
Repeating this construction.
I see.
So gamma r minus 1 is defined by the multiplicies of fibers and gamma r minus 1. Coefficients of gamma r minus 1. Gamma r minus 2.
Okay. Thank you.
So gamma is determined by modifier spaces. I stop here. Thank you very much for listening.
So any question?
I have a question. When you apply this case one to the proof of phenotypeness, could you go back to the I guess
This slide?
maybe one previous slide. Yeah. So delta 1 prime is constructed by using the first sequence. So is it the same? But you have to apply the case one to the sequence y to x1 prime to x2. So delta 1 prime is constructed before you construct y. So is it the same divisor when you construct it by using y?
Yes. So but we have to prove that. So delta 1 prime is definition of delta 1 prime is the strict transform is of delta 1.
Yeah.
And the definition of delta 1 is using the multiplicities of fibers.
Mm-hmm. Yeah.
And in this case, this delta 1 prime is coincides with the divisor defined by the multiplicities of this modifiable space.
Oh,
We have to
so because it's just a flip and birational. So
yes.
okay,
Exactly.
okay, thanks.
Exactly.
Any other question? I have a question. Why you only have flip involved here? What about dividual contraction?
Yes, we have to consider this case.
Okay.
I only introduce the flip case.
And then can you go back to the case one proof about H1 and H, the very final slides?
Yes, right?
I want to know the relationship between your H and H1. So you say H is constructed by H1. So H1 is anti-ample, but H1 is ample, and the H, how do you construct H?
Okay. H is constructed by now it pi y modifiable space from y to y1, and H1 is divisor on y1 and contained by R gamma 1
It is ample.
and relative ample over Z. In this case, we consider the divisor 1 over m rg plus 1 minus 1 over m pi pullback h1.
Okay.
This rg is high relative ample because pi is a modifiable space, so minus ky is ample, and relative pical rank is equal to 1, so ramification divisor is also relative ample. So if m is for large enough m, this divisor is relative ample, Z relative ample.
Okay, I see.
And this is contained in Rg because Rg contains in pi pullback of R gamma 1. This property is very important.
Okay, I see.
Okay.
So in your main, so in your proof, you say you can always run the MMP. First is simply birational MMP, and all the left are the final contractions. Yeah.
Yes.
And
you only use MMP for not Shou effective pairs.
Any other question? Oh, so if the variety, for example, if your X is starting with a variety of phenotype or pheno, so no need to run any MMP, right? I mean,
the first X is phenotype. X
or maybe I should ask it in this way. So if you change your int-amplified endomorphism G with another int-amplified H, so your end product Z are the same. I mean, are they the same?
I see. Yes. You mean this diagram does not
depends on G.
Depend on endomorphism.
Yeah. Okay. Any other question? Okay, if there is no further question, let's thank the speaker. Okay, very nice talk. Thank you very much. Okay, so this is our last talk of this seminar due to my limited funding. So so maybe if I have more funds, maybe I can try to formulate another short seminar. Okay, thank you very much for all of you to attend this seminar. Thank you very much. Okay. Okay, see you. Okay, I'll end this talk. Okay, bye.